Hi, I'm Reinhard Grassmann, and I will present a dataset and benchmark for learning the kinematics of concentric tube continuum robots. First of all, let's meet the robot. Our concentric tube continuum robot, as shown here, is a compact robot composed of 3 carriers. Each carrier has one concentric and precurved tube attached to it. Those tubes are nested into each other and made of super flexible nitinol alloy. Each tube can be translated and rotated with respect to each other. Due to the elastic interaction of the nested tubes, we can create complex shape while being compliant, as shown here, where a hand is interacting with the robot manipulator. In order to model those complex deformation of the nested tubes, we can choose between physics-based modeling and data-based modeling. The gold standard in physics-based modeling utilizes the Koszalot rod theory. The derived boundary value problem is solved numerically. This leads to high computational cost and high modeling effort. To reduce associated cost and effort, physical phenomena such as friction and tube clearance are often neglected. In contrast, data-based modeling approaches are computationally fast, and physical phenomena which are hard to model can be considered with relatively low effort. Therefore, we gathered data from a prototype and learned the forward kinematics. The depicted table lists the accuracy of the gold standard, our new approach, and for comparison, results stated in the literature. The values to beat are around 3 mm in the tip position, corresponding to a relative error of around 2%. Those values can be achieved with the gold standard approach. With the database approach highlighted here, we achieve a better accuracy by 1 margin. But there's something fishy. Do you have access to the dataset, and therefore can you produce the results? Anyway, at least we compare our results with the literature and show that the achieved results are comparable or even better. But again, there's something fishy. Is it a fair comparison if every result is based on a different dataset, and why are they different in the first place? One reason for this is that a large variety of prototypes exist in our research community. The reason and consequences are explored in our previous study. To address the lack of accessible dataset and reproducible results, we provide the first public dataset on concentric tube continuum robots. We gather data from a concentric tube continuum robot prototype with 3 tubes. The dataset consists of 100,000 data points recorded in 8 sequences. Each data point includes 4 poses, all joint values, and their differences. The setup with the robot prototype and the measurement device are depicted in the figure. Furthermore, in this paper we share our lesson learned and discuss open challenges. Both reflect the current state in the literature and our research journey highlighted by the shown publication. Let me briefly highlight 2 lessons learned. First, joint space as well as task space representation really matters. We showed that effective representation leads to higher accuracy and fast convergence in learning kinematics. More importantly, advantageous representation are mandatory even for low-dimensional machine learning applications. Second, placing sensors at each distal end of a tube leads to a practical sensor placement. This allows for variable length, adding of safety margin, and applying the advantageous disentanglement transformation. While in the present paper we only utilize the tip pose, future work will exploit also other information in the dataset, such as the recorded sequences leading to a path and pose measurements along the shape. However, our long-term vision is to feedback gained insight to improve physics-based modeling. This is our final destination, and I invite you to join the journey to leverage the dataset for further improvement. With this, I would like to thank NSERC for the financial support and my colleagues, Nan, Vincent, Sven, Ryan, and especially the director and PI of our lab and my supervisor, Jessica Burgner-Kahrs, for being part of the journey, and I hope you will join us too.